Okay, so now we'll start doing an example of Doppler effect. So here's a typical example that you could get in an exam question. A siren with a frequency of 2000 Hertz is emitted from an ambulance which is traveling at a speed of 60 kilometers an hour. Calculate the observed frequency in front of and behind the ambulance. The speed of sound you can take as 330 meters per second. So as always, when you're doing these kind of questions, what you want to do, you want to start with your equation. Now the equation will be given to you in the data sheet, and I said to you it'll be given to you in this format. Alright, I've left the colouring in here as from my previous expression. So if we're now going to work in front of the car, of the ambulance, we know that the observed frequency must increase, and so this ratio must increase. Now, since it doesn't tell you anything about the observer, you assume the observer is standing still, and in front, if you're going to work first in front of the ambulance, then you know that the frequency is going to increase, and so this fraction must increase. The only velocity you've got to work with is the velocity of the observer, because the velocity of the source, which is the ambulance, because the observer is standing still. So this top bit's going to fall away, it's going to be left with v, and on the bottom you need to make a change that is going to increase this fraction, and so you need to subtract the velocity of the source, so you're going to use the minus. When you do these examples, always quote the equation as it is first, and then change the values as you need them. So I'll take you through it quickly. If we're going to work in front, I've been naughty here, I should have written the equation down first before I used it, but I haven't done it. Apologies for that. You should always do that, write this down first and then do your answer. So I'm calculating there's the speed of sound. I'm adding 0 to it in the front because the observer is standing still, we assume, and then I'm going to subtract the speed of the of the source. Now they said 60 kilometers an hour. I've obviously converted that to meters per second because we're working with the speed of sound in meters per second. And you remember, to get from kilometers per hour to meters per second, you divide by 3.6, and that gives you 16.67. So you put those values into your equation, push all right. Oh, sorry, and then you've got to also multiply that obviously by the fs, the frequency of the source. And the frequency of the source, you were told here, is 2000 Hertz. If you push all the right buttons on your calculator, you should land up with this number there. Now, don't just take my word for it, please do it yourself, because it's very easy to make a mistake at this point. I know it's basic, it's bod mass, but this must be subtracted by these two things subtracted from each other. Now, if you just type this and then divide and this and minus this, you won't get the right answer. So you need to make sure that when you do this in the calculator, you actually get the same answer I do. Multiply your final answer there by 2000 and you should get 2106.4 Hertz. Now obviously you should also quote numbers to 2 decimal points. I've been naughty there again as well. Is that what we expected? Yes, well, we expected the frequency in front of the ambulance to increase. The frequency was 2000, the frequency has now gone up to 2106, so that's what we expected. Behind, we expect the frequency to decrease. So if we move on here, how would marks be allocated? Well, there would always be 1 for the formula, then there'd be at least 1, maybe 2 for the substitutions, and then again 1 for your answer, including the units. Behind, your calculation is very similar, using the same formula again. Substitute the speed of sound, hasn't changed. There's still no velocity of the observer, but now you're talking about an observer behind the person, behind the object, and so the source is moving away. If the source moves away, it needs to decrease this fraction. In order to decrease the fraction, you have to add on the bottom. So now we're adding that same velocity here and then multiplying the answer by the original frequency, and that gives us a lower frequency. So you can see the actual frequency is 2000, is in between these two. In front of the ambulance there would be a higher frequency observed, and below there would be a lower frequency. And again, that could be another 3 or 4 marks. So that's how you would do a calculation. Right, I think I'm going to stop this there to make sure it's working, and you can actually go and try a few. The next little video is going to actually talk about some further applications of Doppler effect, but you need to go and practice some calculations and satisfy yourself that you can calculate frequencies, observed frequencies, and necessary speeds. Remember, we could give you this equations either way around. We don't have to ask for FO. There's 1, 2, 3, 4, 5 variables here. We could ask you any one of them if we gave you all the others. So the questions can get quite tricky. Go and see how many you can do, and when you done with those, you might want to come back and look at the rest of the videos, which will deal with some applications of Doppler effect.